Symphony this life, trying to make ends meet, trying to find somebody in the dark. Take you down the only road I've ever been down. You know the one that takes you to the places where all the things meet. Yeah, no change, I can't change, I can't change, I can't change. But I'm here in my mode. I am here in my mode. I'm a million different people from one day to the next. I can't change my mode. No, 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 no.
All right, let's go ahead and kick things off tonight with that lecture survey question. So a little bit more involved one today. So we were considering a firm with a technology given by this general Cobb-Douglas form here, where we have alpha and beta are given to us as positive productivity parameters, positive because if not, then they would not be a monotonic relationship that is captured. They're facing constant unit input prices, W and R, which we will always assume are positive. Nothing's being given away for free. And the question was asking about the firm's long run conditional input demand for labor. And you're given these 4 different demand functions to choose from. And it might have been a little daunting. You're like, man, am I going to have to solve a problem like that, in about 5 minutes? Like you might in a quiz situation. Yes, that is something that should be reasonably done in about that amount of time. Now, if you didn't want to solve the question and you were seeing if there's maybe an easy way out looking at the answer choices, there's a pretty quick way I think you can eliminate some bad answer choices, right? If these are demand curves, what should happen for the demand for labor as the wage goes up? Should go down, right? Opposite direction. So you should be able to look and see that there's a couple demand curves where the wage shows up in the numerator, right? Wage goes up, causes the demand for labor to go up. Does not make sense. Okay, so you can get rid of those. Between the other choices, okay, the remaining 2, it's difficult to discern. All right, so I'm going to actually solve that problem in its entirety in just a moment. If you were in the quarter of students who got this one right, nicely done. I did want to mention the quiz performance for this past week. It was definitely improved from last time, so nicely done. The average score here was above a 70. High scores were quite a few hundreds, low scores at the other end of the spectrum. Pretty volatile exam. People were off from the average about 2.5 points above or below. And just note the overall distribution here. So again, average score, it's going to curve somewhere to around a B- at the end of the day. So you should be looking at these every week and kind of gauging where you are in that distribution moving forward. Also, do not forget about submitting your self-proctoring links. The TAs had let me know there were still quite a few issues with that, people not having the proper sharing permission set on their Google Drive. If you're submitting links and the TAs cannot access them, not going to be a good situation. So they may reach out and just give you a gentle warning if that is the case. If you didn't submit any link at all, you should expect at the end of the term that we will just use a 0 for that assignment grade instead. We're not going to change it up in the grade center in real time. So please make sure if you ran into any technical issues, this is the 3rd quiz assessment. You should have had those ironed out in the technology check practice quiz. The leniency is fleeting on those types of issues. So make sure you're getting those recordings in prior to midnight, the Tuesday afterwards, into that bottom module. You just submit the shareable link to your Google Drive. Do not submit links to the Zoom cloud files. That is not what was in the instructions for the protocol of self-proctoring. If you've been submitting links to the Zoom cloud repository files, then you're not getting credit for those because you're not following protocol. So just double check the protocol. Make sure you are following it unless you reached out to me and you were given specific exceptions, and you would know if that is the case. With that being said, let's go ahead and pick back up with our discussion of cost minimization and cost functions. I think this is approximately where we had left off last time. So we're going to pick up with the agenda today of dealing with specifically the problem of long run cost minimization, which is where we had, I think, just left off last class. So we're going to pick that up. We're going to go through an example, specifically the example we had just dealt with in the LSQ, where we're going to derive not only the conditional input demand for labor, we're going to figure out what it is for capital as well, and then we're going to put those together to calculate the total cost of those input demands, which is how we're going to generate that long run cost function. And we're going to revisit the idea of returns to scale and see how, in the specific context of this Cobb-Douglas model, how the returns to scale plays a role in influencing the shape of the cost function in what turns out to be a very general sense, even more general than just what is confined to the context of the Cobb-Douglas example. We'll talk about comparative statics of price changes. What happens when the relative input prices change? How does the firm think about reallocation of its input bundles, given that it may have some output objective that it needs to satisfy? So that is the focus of today. Next class, we're going to talk about some subtle issues with cost minimization and some intricacies associated with doing things like recovering the underlying production function, starting with a cost function, rather than going in the opposite direction, which we normally have done. Right now, we start with the production function and we solve an optimization problem to think about getting the input demands and then getting the cost function. And then optimization problem we had formally outlined last class, where we were trying to minimize the total expenditure on our inputs subject to our technological constraint. And again, this was the long run problem. So we did not face that extra short run constraint that capital was equal to some constant. We're going to go ahead and set up the Lagrangian today to solve this problem, so we can kind of see the full set of conditions in a 3x3 framework where we have 2 inputs, but we introduce a Lagrange multiplier. And again, that Lagrange multiplier functions to play an important role in capturing the differential behavior along the boundary of that constraint set. The constraint set in this case being T, this green technology set that we are looking at. So the way we're going to solve this problem in a moment is we're going to take 3 first order conditions, right? One with respect to K, one with respect to L, and one with respect to lambda. Okay, the lambda first order condition, though, that will give us back our constraint equation, which was one of the equations we said had to be true in the optimal solution. So once we take those 3 first order conditions, we will have a system of 3 equations and 3 variables, and we will be able to then solve that system to find the conditional input demand functions for capital and labor. So we spent a little bit of time last class characterizing the optimum graphically, at least in terms of our three-dimensional technology. And graphically, we recognize that two important features define the optimal cost minimizing input bundle. And that was if we were actually on the lowest ISO cost curve, meaning that we were just tangent to that technology constraint, then number one, we had a mathematical condition to describe that tangency. And then number two, we had an isoquant equation we could work with, right? Which, using the Lagrange method, we will always get equation number two from taking the derivative with respect to that Lagrange multiplier. So this is the idea we were looking at last class, was that we had these ISO cost lines. Along those lines, the cost of the input bundles were constant, but the goal was to minimize the cost. So we wanted fewer inputs, right? Lower ISO cost curves, subject to still being in that technological constraint set, which put us just tangent at the optimal bundle of inputs. So we solved this problem graphically last time by first identifying the tangency condition. Okay, in our Cobb-Douglas example, the tangency condition happened to be a linear equation that described the set of points in the entire isoquant map where the slope of the isoquant map equals the slope of the relative prices implied by the slope of the isocost curve. You may get tangency conditions that are not a straight line, that could, be nonlinear functions, but we may also refer to this as the output expansion path. If we increase the level of output at the same input prices, we would expect to traverse that red line across those tangencies, right? The tangency along that isoquant map. So the tangency condition, that gave us one important equation, right, graphically, to identify the solution. But the other equation that had to be true was the actual isoquant equation for the isoquant that applied to the output level that we were defining as our objective in that constraint, which is Q bar. So once we have the right isoquant equation to pin down that level of input usage along the tangency, then we should be able to just kind of look here and see, hey, the red curves intersect at a point, and the point they intersect corresponds to the cost minimizing bundles. Okay, so you could solve it graphically, you could solve it, numerically, mathematically, using Lagrange. Unless you're told to do it one way or the other, you have the freedom to pick. I think there was a question in the last quiz that just asked you to identify the form of the Lagrange problem. But if it doesn't, you have the freedom to do it whichever way is more comfortable for you. Now, you should also hopefully, given my hint last week, or looking at those work problems as well as the practice exams, and kind of noting, hey, there are some situations where maybe we have things like kinked isoquants, L-shaped isoquants, where calculus will not work, and you have to use some graphical analysis and intuition to solve the problem. So what we're going to do today is we're going to spend most of the time looking at the example where we derive the long-run cost function for a general Cobb-Douglas technology, which looks exactly like the problem we had dealt with in that lecture survey question a moment ago. So if you're wondering, is he going to actually solve for the labor input demand function? I will do that. I will try to go fairly deliberately to do that, and then we'll find the capital input demand function. And then the way we're going to get the cost function is essentially the same way we did in the short run. Once we have those input demands, is just by plugging them in to the expression for the total expenditure on those inputs. So let's assume very generally here that the prices of capital and labor, they are constant, and they're just given by the vector WR, right? W for the wage, R for that rental rate on capital. And what we want to do then is write out our optimization problem, and I will do this mathematically using the full Lagrange technique here. So mathematically, right, we have our total expenditure, right? That is our objective here, WL plus RK. That's what we want to minimize. Okay, we have our constraint in the blue box and our Lagrange multiplier in front of the constraint, highlighted there in pink. Okay, so step one, want to solve the problem, have to write the problem down, right? So there is our problem written down. Step two, okay, we want to solve the optimization problem. So we're going to take the associated first order conditions. Okay, so first, let's go ahead and take the derivative with respect to capital. Okay, notice the only place capital is showing up is multiplied by r in the objective function, and then it also shows up in the constraint inside the production function. So if we take the derivative, right, the partial derivative with respect to k, this whole first term with w and l goes away. Right? Then we get to the second term, r times k, and the derivative with respect to k just leaves the constant r behind. And then we get to the last term, right, in the constraint, q is going to go away because that's a constant, right? And then we get here, and the derivative of the production function with respect to k, we should know how to interpret that, right? If you take the derivative of the production function with respect to k, that's the measurement of what? What is that measuring? Yeah, that's right, Bryce. That is the marginal product of capital. Okay. So if we go ahead and take those derivatives, yeah, if you have any questions about the quiz problems, definitely come to office hours. That is where I will go through those, but I have something very specific planned for class. But if you have questions about that, myself, office hours, TA's got office hours, that is exactly what those are for. So please drop in, let us know. Happy to help. Now, if we can solve the problem with calculus, right, where we don't have something like the min function. Okay, again, if you had some trouble with that min function on the quiz, I would take a look back at how we dealt with the min function before to think about where the corners of the min function have to be. That's a really important part of dealing with those perfect complements case there, Elizabeth. So if you go through and look at that, and then you want to meet me in office hours, I'm happy to go through that question with you. No problem there. Now, taking the first order conditions with respect to K, what we're going to wind up with is the following. We get the rental rate on capital, right? R we said stays. And then we have our value lambda here, okay, which is that, that Lagrange multiplier. And then we have lambda multiplied by the derivative of the production function in blue, which we just said a moment ago was the marginal product of capital. Okay, then what we're going to do is we'll take the derivative in the labor direction, right? We're looking at a three-dimensional function we're trying to like minimize. So we want to make sure we're in the, we have a zero slope no matter which direction we walk, left, right, front, back, right, north, south, east, west. I'm taking the derivative with respect to each of those three variables, setting them equal to 0. So when we take the labor derivative, notice if you look at the objective function, here's the only term in the objective that has a labor in it. So L goes away, we're left with W right down here in the blue highlight. R times K, that term is again going away because there was no L in it when we take that partial derivative. And then we take the partial derivative of that production function again with respect to L. That gives us the marginal product of labor multiplied by that Lagrange multiplier lambda again. Okay, last but not least, we take the derivative with respect to lambda. When we do that, what are we left with? What are we going to be left with? Yeah, we'll just have that constraint, right? Our technology equation, that comes back. Okay, so step 2, we took our first order conditions. And now you'll notice we have a system of exactly 3 equations, and we have 3 unknowns, K, L, and the multiplier lambda. Now, we could solve for lambda, but we may not be that interested in the value of lambda, right? What we're really after is the capital and labor cost minimizing input values. Okay, so what we're going to have to do from this point, and again, once you get here, there are a number of different ways you could find the solution. But in order to get the solution, you're going to have to solve this 3x3 system in some way, shape, or form. Okay, I'm going to recommend a particular way to do that that'll be consistent with how we solve the problem graphically. Okay, specifically, if you take these first 2 equations and you combine them, you should be able to use those 2 equations to combine them in a way that gives you the condition that describes the isoquant being tangent to the isocost curve. Okay, the last equation, hopefully is obvious, is just our constraint. So if you have the tangency condition together with the constraint, those were the 2 things we said we needed graphically to identify the solution where they cross. So whether or not you're using Lagrange, whether or not you're using the graphical intuition approach, you wind up at the same place. You wind up with the same solution. So let's go ahead and in step 3, we're going to go ahead and deal with the tangency condition. Okay, so let's combine the first 2 first order conditions to get that tangency condition. When we do that, okay, I'm going to eliminate the lambda variable from the problem. I'm going to just get rid of it. Okay, so that we then have 2 equations with 2 variables. We'll have the tangency condition and the isoquant equation, and we'll be able to solve for capital and labor without worrying about that multiplier showing up. Okay, so again, that third first order condition, that gives us that isoquant equation. And let's deal with the first 2. So here's what I want to do. Let's take the first 2 equations. Question is, isn't it simpler to just solve for the tangency condition without the Lagrange? Maybe if you only had 2 inputs. But if you had like 10 inputs, then the tangency condition is not going to make a lot of sense because you have a 11-dimensional technology and you can't really solve it graphically. So I'm going to try to give you the intuitive approach that works in our 3D model. And I want you to be able to see how, if we were using the numerical method, which applies in any situation, that you get the same conditions that we get with the graphical approach. So Dylan, whichever approach you're more comfortable using, if it's applicable, I want you to do what's ever more comfortable. But there may be situations where you're limited to using one approach or the other. Hope that makes sense. Really good question, by the way. Now, what we're going to do here is we're going to take the first 2 equations and we're going to simplify them to get rid of the lambda. What I'm going to recommend we do is take both of the terms that are showing up as negative in those equations. These are both of the terms in orange. And I'm going to say, let's add them to the other side. Okay, let's take the 2 terms, add them to the right. So no more 0 on the right. And when we do that, we're going to be able to divide the equations by each other to eliminate the lambdas. And so that's where we're going. We have our 2 first order conditions. Okay, notice I've slightly rewritten them here because we recognized a moment ago that the marginal productivities popped out. Those were key conditions in when we assess the tangency condition. So all I'm going to do here is I'm going to take the terms that are negative, that have the minus, and I'm going to add them over to the right-hand side of the equation. And then we're going to divide the top equation by the bottom. So if we do that, okay, if you're looking at the green box, let's first add those negative terms to the right. So there's no more 0 on the right-hand side. Okay, no more 0 on the right-hand side. Only thing that is on the right-hand side are the marginal products times the lambdas. Okay. Next step, to get rid of the lambdas, I'm going to divide the top equation by the bottom equation. Hopefully you see that when we do that, the lambdas will cancel. And then on the left-hand side, we'll have W over R, or R over W. And on the right-hand side, we'll have the ratio of the marginal products. Okay. So here is what that looks like. Okay. We divide them. So, right, we get W over R equals MPL over MPK. That is literally the tangency condition from before, right? The slope of the isoquant in absolute value equals the slope of the isocost curve in absolute value. That is our tangency condition. Okay, note that we can rewrite that tangency condition a little bit. Okay, solving for the y-axis variable. And we can see specifically that that thing is a straight line, right? Alpha is a constant, beta is a constant, W is a constant, R is a constant. So that's an upward sloping straight line through the origin. And the slope of that line, since we have K on the vertical axis, has to be the coefficient on the x-axis variable. Okay, so that is that yellow dotted line that we were seeing on that picture a moment ago. That is the tangency condition. Okay. The next step is we're going to combine that tangency condition in red with the isoquant equation. Notice we got rid of the lambdas. So now we have 2 variables left, and we're going to have just 2 equations to deal with, right? One is the tangency condition we had from before. The other is the isoquant constraint. So all we need to do now is take this expression for capital and we'll plug that in for K below. Okay, that will give me an equation where we've eliminated K, and the only variable from our optimization problem that will be left is L, which we will be able to solve for. So if we plug that in, the constraint equation becomes the following. Right, we have the tangency condition essentially to the alpha times L to the beta there. And we should now be able to solve that resulting equation for L. Okay, in fact, let's do that. We have an L to the beta on the outside. We have an L that's actually raised to the alpha power on the inside. Good question. What did I plug in last slide? We plugged in the expression for K along the tangency condition. And we plug this thing here into K here, right there. I'm very, very literal with how I make my arrows. Very literal. Okay, so I'm just plugging in that thing from the tangency condition into there. Now, if you solve the tangency condition for L, you can do that too. You would just have to plug it in for L in the isoquant equation. So again, many different ways you could go about getting the solution. This is one of them that I'm outlining here step by step. So once we do that substitution, we have one equation with labor as our only variable. Okay, and what we could start to do here is collect our terms. So I'm going to argue we have an L to the alpha times an L to the beta. That is the same thing as L to the alpha plus beta when I combine those 2 labor terms above. Okay, now our goal is to actually solve for L. So the next thing I'm going to do is I'm going to raise both sides to the 1 over alpha plus beta power. We're going to take both sides and we're going to raise them to the 1 over alpha plus beta power. We're going to do that to both sides. So left side that happens, right side that happens. When I do that, you should notice that exponent is going to cancel with the exponent on L. I will be left with just an L. Okay, we will distribute the exponent in to this alpha that is raising all those other constants, right? Beta over alpha times R over W. And then we're going to have to move Q to the other side. We're going to have to move alpha, or sorry, we're going to have to move some terms to the other side. Okay. So if we were to do that and we solve for L, okay, here is what you wind up with. A little bit of algebra, we solve for L. So this is the answer to the lecture survey question for today. Okay, that is how we got there. We used the first order conditions, we combined them, and doing so yielded the tangency condition and the isoquant equation, right? Which we said we can solve in order to find those optimal input bundles. Now, our goal here is not just to find the input demand bundle for labor. The goal was to derive the long run cost function for this firm with this technology. So we're part of the way there. We have our demand for labor, okay, as a function of Q. What we need to do next is figure out our demand for capital. And there's again a few ways you could do this. Given the demand for labor, good question. Why did alpha and beta get switched and R and W get switched? So if you go back a couple steps, okay, what I'm going to be left with here, if you look at the purple box on that second line, I'm going to have an L on the right-hand side, which means I have to divide everything else over to the left. Is that clear? I have to move all that other stuff over to the left. So look carefully. We have alpha over beta, W over R. If I move that to the other side, what's going to happen to those fractions? Going to flip, right? I'm going to take the reciprocal. So that's why the alpha and the beta and the R and the W are flipped compared to the line above. We had to move them to the other side to get the L alone. Okay, and then I flipped everything back, which is why the L's on the left again in that bottom line there. So I hope that answers your question there, Elizabeth. Please feel free to follow up with me again. If you need any clarification, happy to. Now, once we have our input demand for labor, I can take that and I can plug it into either the tangency condition or the isoquant equation. Remember, they both cross at the solution. So I can plug L star into either one, and that should give me K star. I'm going to go ahead and I'm going to use the tangency condition. Okay, tangency condition said K had to equal alpha over beta times W over R times L. So let's just take our expression for L star, which is everything in the yellow here, and let's just directly substitute that for L star directly into the tangency condition. Okay, and when we make that substitution, here's what we get. Okay, and again, there's some things that it looks like we might be able to cancel. All right, so note there's an alpha over beta W over R. Here is the inverse of that same term. Okay, so those are going to be things that we'll be able to kind of cancel some stuff out and simplify the exponent there. We can do that in the next step. Okay, alpha over beta times W over R, this term in the purple. That's the same thing as the reciprocal, but to the -1. Is that right? The terms in the purple are exactly the same thing. Any questions about that? And now what we can do is, recognizing we have the same base, right? Same base in the purple here. Same base, same base. Then we can add the exponents together, right? If we have the same base, we can take alpha over alpha plus beta. We can add it to -1 and we can get a common denominator there. And here's what that looks like. Here's the alpha over alpha plus beta, and here's the -1, right? We're getting a common denominator there. And then we're going to go ahead and just simplify that a little bit. Yep, so I'm going to just simplify the numerator. I have an alpha minus an alpha plus a beta, which is going to leave me with just a minus a beta up top. And to make sure we don't have any negative exponents, I'm just going to rewrite the inside fraction. I'm going to flip it upside down again. Right? If you flip the fraction upside down, then you can make the exponent negative of what it already is. So here it is. We flip it upside down. And notice we go from a negative exponent on beta to a positive, or sorry, a negative sign in front of the beta, a part of the exponent, to a positive sign in front of that exponent. And what we're left with is our conditional input demand for capital. And so what we've done here is we figured out the cost minimizing combination of K and L as functions of the prices of the inputs and the level of output that we are desiring to produce, right? The level of demand we need to meet, if you will. But our goal was to get the cost function. So what we can do now is we can take our solutions to the minimization problem and we can compute the total expenditure on these two input demands. Okay, so we have our two input demand bundles, the solution to cost minimization. If we want to compute the cost function, we just say, well, how much do these things cost? The labor expense, right? We know that is W times L. The capital expense is R times K. And all we're going to do is plug in our capital and labor input demands into that cost function. And things get a little messy. Okay, they do. But if you're careful and you simplify, it gets a little bit cleaner. Okay, it gets a little bit cleaner. And I'm going to redefine some things in a moment. So we're not looking at a ton of constants being multiplied by each other. I'm going to come back to that in just a second. So step 5, right? This is very similar to how we found the short run cost function, right? We take our input demands and we figure out the expenditure on them. We plug them into that total cost expression. And once we're here, we can do some simplification. And for example, there is a common factor in both terms. You should see that there's a Q to the 1 over alpha plus beta in both expressions. I can factor that out. So here that is factored out. Okay, and then everything that's left in the front. What can you tell me about all the numbers or values that are left in that pink box? What types of values are they? All alpha, betas, W's, R's. They're all what? Yeah, they're constants. Is that right? They're all constants. Okay, so my point here is all that stuff in the pink, it's something, but it's a constant. Okay, and that can be simplified a little bit, but again, not super concerned because it is a constant. Okay, it is a constant. So here's what I'm going to do. So we're not looking at that big, ugly constant in pink. I'm just going to define that whole thing as a new variable, okay, a new constant. And that'll let us write it a little simpler. And then we can really look at, well, what's the relationship between C and Q? And that's really what we're going to focus on in a moment. So we have now the total cost function expressed as a function of Q, and that is consistent with the firm that is minimizing its long run costs for both capital and labor are both variable. All right, so here's what we're going to do. Okay, we given the conditional input demands, we found those by solving the cost minimization problem. Okay, and we found our cost function by valuing and finding the expenditures of those conditional input demands. Now, this term out in front that we were talking about a moment ago, the term in red, okay, that is a constant. So what I'm going to do is I'm just going to use the variable omega as a placeholder for that constant. That is the placeholder. Okay? So this whole cost function is some constant times Q to a power that depends inversely on alpha and beta. All right. So here's what we're going to do. We're going to think about now plotting this cost function. We're going to plot that cost function. And you'll notice the shape of it probably is going to depend critically on what? What is the shape going to really depend on? Yeah, Isaac, I like what you're saying. Yep. The alpha and beta's values are going to be super important in terms of what the shape of the cost function will look like. Okay. And I mentioned that we were going to revisit the issue of returns to scale today. So hopefully you remember how alpha and beta affect the returns to scale of a Cobb-Douglas function. Right? If alpha and beta add up to 1, everyone remember what case that is? We discussed that case explicitly in class. Alpha and beta add up to 1. Yeah, that was constant returns to scale. That's right. But if alpha and beta added up to more than 1, then you double the inputs, you get even more than double the output. That was what? Yeah, that was increasing returns to scale. That's right. And if alpha plus beta was less than 1, then we double the inputs. We don't get quite as much as double the output, and we would face diminishing or decreasing returns to scale. That's right. So what I want us to think about here is the sketch of the cost function and the implications of how the returns to scale property of the underlying technology influences the picture, the cost structure of the firm here. So the first case that we're going to consider here is if alpha plus beta is less than 1. Okay, that's the case of diminishing returns to scale. If alpha plus beta is smaller than 1, what can you tell me is true about that exponent in the green circle? It's got to be true about that. If alpha plus beta is smaller than 1, then the inverse of alpha plus beta has to be what? Yeah, gotta be greater than 1. It has to be greater than 1. Right, so if you have Q to some power greater than 1, right, the X variable to some power that's bigger than 1, like X squared or X cubed or X to the 3/2. Okay, hopefully you have an idea of what the sketch of that graph is going to look like. Yeah, it's going to be upward sloping, and the slope is going to get steeper and steeper as we increase our quantity produced. So if you face decreasing returns to scale, what can you tell me happens to the marginal cost of production? Like, what happens to the marginal cost if we produce more and more here? Yeah, it's going to go up. That's right. And we could calculate that, right? We could take the derivative of the cost function with respect to Q. The exponent comes out front. So we get omega times 1 over alpha plus beta, and then we subtract 1, right, from the power there. Yeah, so we can compute the marginal cost, and we should recognize that that exponent on the marginal cost expression, if alpha plus beta is smaller than 1, then that is going to be bigger than 1. So we should see here our marginal cost actually increases as we increase Q. Okay. However, if we had a constant returns to scale technology, what would be true about that exponent in the red in the bottom if we had constant returns to scale? Then the exponent in the red would be what? It would be 0. And then you get Q to the 0 power. Anything to the 0 power is what? That's right, 1. So if that were the case, the marginal cost wouldn't even depend on Q. It would be what? Yeah, it would be constant. It would be omega, right? It would just be that constant. Okay, so if we were in that case where alpha plus beta equals 1, right, then if we plug the 1 up here for alpha plus beta, what will that graph look like if it's Q to the 1 power? What type of graph is that? Yeah, it's going to be a linear graph. It's just going to be a straight line. Okay, so again, if we were to compute the marginal cost, if alpha plus beta equals 1, then the marginal cost just breaks down to omega, and the slope of that function will be omega. That's going to be the slope. Okay, so the marginal cost is just constant no matter what level of output we produce if we have a technology that satisfies constant returns to scale. We get this flat marginal cost function corresponding to a linear total cost function. Okay, last but not least, if alpha plus beta is greater than 1, meaning we face increasing returns to scale, then that means this exponent is going to be smaller than 1. And if that exponent is smaller than 1, then we're going to get a graph of cost where it looks like the marginal cost diminishes. Okay. Marginal cost is diminishing here. Right? Starts out pretty high, but as we increase output, the cost of each unit gets cheaper and cheaper and cheaper and cheaper. And you get a decreasing marginal cost as Q goes up. So very important relationship that we can kind of see here between returns to scale and the underlying cost function for the firm that is minimizing their long-run costs. Now, what we're going to do next is we're going to shift gears a little bit, and we're going to look at how does the firm reallocate its inputs when it faces a price change, right? Economic environment is rarely constant. And in fact, change is probably the only constant. So we want to know when the economic environment changes, right? Like if there's some change in input prices, for example, okay, what does the firm do to respond to this? So let's go ahead and take a look at an example here without too much loss of generality. And let's suppose that the rental rate increases relative to the wage. Okay. If the rental rate increases, that means the slope term is going to get smaller in magnitude. Everybody okay with that? The absolute value of the slope of the blue line is going to get smaller, meaning the ISO cost curve will become flatter. Okay? And what will actually happen is it will pivot around the point that we were currently producing. Prices change. We were producing this thing, so the thing we produced is still on the same ISO cost curve, but that ISO cost curve is now flatter. Okay, if I ask you the question, for the red ISO cost curve, is K star L star still the optimal solution to the cost minimization problem? What's the answer to that question? Yeah, K star L star is no longer the optimal solution once the prices have changed in this fashion. Okay, our goal is to get to the lowest ISO cost line, and we can see here that red one is not the optimal bundle anymore. Okay, we have an old optimal bundle, but if the firm's going to re-optimize, now that capital has gotten more expensive relative to labor. If capital is more expensive relative to labor, what's the firm going to do with its allocation of capital and labor relative to the initial bundle? Yeah, it's going to shift towards more labor and cut back on its usage of capital. That's very good. Okay, so it's going to substitute, meaning we're going to witness here a pure substitution effect, a no income effect when you're considering price changes with a cost minimizing firm. We don't have to worry about any of that weird Slutsky equation, income effect, substitution effect, not an issue here. Cost minimization, there's only a pure substitution effect, and we can identify the new bundle by just reapplying the tangency condition at the new set of input prices. So we went from the old bundle, which had relatively more capital, less labor, to the new bundle, which has relatively more labor and less capital after the prices had changed in the way we described. Now, there's a couple important properties of cost functions that we're going to spend some time talking about on Thursday. One of the properties is related to homogeneity. And we talked about the homogeneity property in an earlier segment in relation to the returns to scale concept. And I wanted to revisit that again today to think about the homogeneity property applied to things like our conditional input demands, as well as our cost functions. All right, so hopefully you remember if a function is homogeneous of degree alpha, you can scale all the inputs up by some factor lambda, and then the output will scale by the factor lambda raised to the alpha power. So we're going to think about the following question here. What happens if both input prices, right, the wage and the rental rate, what happens if we change W and R by exactly the same factor? That's what I want you to think about. What happens to the demand if we change W and R by the same factor. So I want to know what has to be true about our demands for labor and our demands for capital if we were to scale up all the prices of capital and labor by the same factor. What do you think? Okay, good. So I see a lot of folks are saying the slope of the blue line is not going to change. I agree. If the slope of the blue line does not change, right? Because scaling the wages and the rental rate by the same factor means you're going to get a lambda times W divided by a lambda times R as your slope of the new ISO cost curve. So the slope doesn't change. And yeah, we're still aiming for the same Q. I'm not changing that. Still trying to shoot for the same Q. So if the slope doesn't change and our constraint set is the same, what is true about our optimal bundle? It is not going to change. That's right. It means the optimal bundle is still the same. So if we doubled all the input prices or tripled all the input prices or lambda'd all the input prices, that should not change the conditional input demands for capital and labor here. Meaning, when we lambda'd the input prices, we got back lambda to the 0 times the original input bundles. Meaning that the conditional input bundles themselves are homogeneous of degree 0 in input prices. And again, if you need a good review of the homogeneity property, definitely check out the survival guide machinist handout, as well as the relevant IMVH videos on returns to scale and homogeneity. But if we lambda all the inputs, we get exactly the same inputs back. So they are homogeneous of degree 0 in the input prices. Now, a couple other important properties of cost functions that I want to mention today before we're out of here. The input demands are homogeneous of degree 0. I'm going to argue that that implies that the cost function itself must be homogeneous of degree 1 in input prices. Okay. Meaning the following. Homogeneity of degree 1 means if we were to scale up all the input prices by the same factor, then the cost function will also be scaled by that same factor. Okay. I think we should be able to prove this here, so I'm going to go ahead and do that. Okay. Here's the proof. We started with our general cost function, and what we want to do is compare that to the cost function where we've scaled up both the wage and the rental rate by the factor lambda. Now, we just made an important argument about both of these terms in the green boxes. What is true about both of the terms in the green boxes? Yeah, they are exactly the same as the labor and capital values above that are not scaled by lambda. So the labor values in the green boxes are equal to each other. The capital values in the green boxes are equal to each other. Because the conditional input demands we just argued are homogeneous of degree 0. So that means we can rewrite the new scaled cost function using the old input demands. And when we do that, what do you notice we can factor out of this entire term in the bottom? What can we pull out of that whole thing now? What can we factor out? Yeah, we can pull that lambda out in front. Everyone see that? So we now get lambda times the original cost function, okay, which concludes the proof that the cost function has to be homogeneous of degree 1. This is a very general result, specifically in the prices. Scaling the prices for a constant level of output, this has to be true. Okay, so some important properties of this long run cost function. It's got to be homogeneous of degree 1 in input prices. Okay. It should generally be non-decreasing in Q. If you want to produce more, cannot cause your cost to go down due to things like monotonicity. And it should be non-decreasing in input prices. Okay, it should also be non-negative. Cannot have a negative cost. Can have a zero cost, but not non-negative. And it should also look concave with respect to input prices. Okay, so concavity with respect to input prices means if we were to graph the cost with respect to an input price, then we should see that diminishing effect. Okay, the last property we're going to spend a good amount of time talking about next lecture is something called Shepard's lemma. And Shepard's lemma is a pretty neat trick with a derivative. If you take the derivative of the cost function with respect to either input price, then you can actually get back the conditional demand for the inputs. And you can actually recover the conditional input demands from a cost function. In fact, I'm going to make the argument that if you told me the long run cost function, what we can actually do is recover the underlying production function that corresponds to the long run cost function. So right now, we started with the production function, right? Our description of a technology. We assume cost minimizing behavior, and that led us to find a cost function corresponding to that optimal behavior. So at this point, we should be able to understand how a particular production function corresponds to a particular cost structure. Okay, so this process we should be fairly attuned to here. Why do I save these tricks for after the quiz? These tricks will be relevant for the next quiz, I think, too. So I think you'll have some opportunity to use them. Now, let's take a look at this. The process we've thought about so far is we started with the production function as our description of the technological process, right? And then we solved a problem to go from the production function, right, to go from the start to find the input demand. What was the problem we solved? To go from the production function to find the input demands. That was what? Yeah, that's cost minimization. That's the problem we just solved, right? That lets us start from the production function as our constraint, and we can figure out the cost minimizing demands. Once we have those input demands, then we just figure out, well, what's the cost of those input demands? What's the expenditure on those input demands? And that is how we generated the cost function, right? Using this kind of three-step process here. Started with the production function. We solved cost minimization to generate the input demands. And then we computed the expenditure of the inputs to find the cost function. What we're going to start thinking about doing is riding this road in reverse. Okay. You probably learned in consumer theory, right, that there's a dual problem to cost minimization that is the same solution as the utility maximization problem. And this duality can be exploited to our advantage under certain conditions. And I'm going to suggest that the existence of this dual problem implies that we could run the same process in reverse. Yeah, these slides might be from the next lecture. We're just a little bit ahead in that material. So you will see those slides when I post up the slides for the next lecture. So don't sweat this stuff too much for the LRP tonight. These will not really be relevant for that. But this discussion should prep us for what it is we're getting into on Thursday's class. So here's what we're going to think about on Thursday. If instead I started you with a cost function, suppose I didn't tell you the production function, I just said, here's the cost function. Okay. Is there a way that we could go backwards and we could figure out the form of the underlying technology as specified by the production function? And that's what we're going to work on. Can we go backwards? The answer is, under certain conditions, yes. They will be able to go backwards. And there's an important link that allows us to go from the cost function backwards to the input demands. And that link is that last important property we talked about of the cost function, which is Shepard's lemma. Okay. So we're going to really exploit that next class in a way where we can recover our input demand condition. And then what we'll do is, given the input demands, we're going to reverse engineer the tangency condition in a way that allows us to recover a production function. All right. So this important idea of duality is going to come back in full here, implying, again, that there is a two-way street between a production function and a cost function. We saw this in the short run case. We're seeing this again in the long run case. Okay, that there's really multiple ways you could think about modeling or describing a technological relationship. One could be explicitly modeling a production function. One could be explicitly modeling a cost function, which has built into it the underlying technological relationship implied with that cost minimizing behavior. Okay. And in most practical situations, right, like production functions may not actually be known, right? They're highly abstract. It may be easier to describe a technology with cost data. I know how much stuff costs. I know how much I produced. That's a little bit easier than trying to define a capital unit and a labor unit. Okay, if you think about it. So being able to ride that two-way street is going to be pretty important for us in terms of thinking about this dual description of a technological relationship. And I don't want to get too far ahead because you don't have these slides. So this is where I will wrap things up tonight. So if you have any questions, we'll do a little bit of rapid fire Q&A in the chat. If not, you are free to go. Have a wonderful evening. Take care. Stay safe. Make it over that Wednesday hump day. And I will see you here Thursday, same time, same place. Yeah, if you want to ask questions in office hours, please shoot me an email. Just give me a heads up that you're going to come. I do appreciate that. Thank you very much. Again, happy to go over those quiz questions with you in office hours. TAs also have office hours. They are equally capable at answering those questions as well. So if you're waiting around for my office hours to come back and there's TA office hours in between, it might be faster to get your question answered by approaching them as well. But certainly feel free to follow up with me if you ever need to. Otherwise, let me go ahead and hand things over to Uday, our wonderful